Hi folks, this is number 17 from page 419. So they give us these two vectors, the second of which has a couple of unknowns. So in the first one they want us to find the values of a and b that make these two vectors collinear. Okay, so in other words, we have to think that these two vectors are separated by a constant multiple. So that means there has to exist a k such that k times p is equal to q. Or I guess you could write it as k times q is equal to p. Either way. And of course a non-zero scalar multiple. Okay, so this is where I want you to pay attention to the two components which we actually know, which are the z components. Because here, the z component of p has to be 3, the z component of q has to be 6. So if I'm multiplying p by k, that means that negative 3 times my k value has to be equal to 6. Okay, so if I multiply this by k, so multiply the z component, negative 3k has to be equal to the z component there, and so I know that k has to be equal to negative 2. And then from there I can calculate a and b. So a is going to be equal to my k value, negative 2 times the x value here. So that's just going to be equal to negative 4. And my b value is going to be equal to the k value, negative 2, times the y value in p, which is also negative 2. So we're going to have b is equal to 4. Okay? So let's move on to part b, which is condition for p and q to be perpendicular. Now the way they've stated this, it kind of sounds like they're implying that there'll be more than one answer, unlike what we had in A. So again, as soon as you think perpendicular vectors, you should be thinking about the dot product being equal to 0. So let's use that to set up an equation. So we need 2, negative 2, negative 3. Okay, dot q, which is a, b, 6, must be equal to 0. Okay, and when we actually do the algebra here, well, we've got 2a minus 2b minus 18 is equal to 0. Well, we realize that what we end up with is an equation with a and b, so not something we can solve. So if we simplify this, we have a minus b, and here this is going to be minus 9. Let's bring that to the other side, make it look a little nicer. So the relationship between a and b is given by this equation. So as long as a minus b is equal to 9, p and q will be perpendicular. Okay? So in C, they say find, and if you read the question, it says find a unit vector which is perpendicular to P, meaning, again, or implying that there's probably more than one answer. Okay? So in fact, what this relationship gives you is infinitely many vectors that are perpendicular to P. Okay? We need one that's going to be a unit vector. So let's first start by finding some vector Q. Okay? So here, I'm going to take something really easy. I'm going to assume b is equal to 0, so a is going to have to be equal to 9. Okay, so that means my q vector, based on b being equal to 0, is just going to be 9, 0, 6. Now, if you want to check, just to make sure that it is indeed perpendicular to p, let's take the dot product. 9 times 2 is 18. We get 0 there, and there we got minus 18, and 18 minus 18 is 0. So this is a perpendicular vector. Now we want a unit vector that's perpendicular to P. So if we take the vector Q and divide by its magnitude, we're going to get a unit vector that's perpendicular to the vector P. Okay, so the magnitude here is square root of 81 plus 36. So 81, 91, 101, 112, 117. There we go. So here I'm just going to have 9 over square root of 117. This, even if I divide it by square root of 117, will still be 0. And we have 6 over square root of 117. Okay. And there you have it. You have a vector which is perpendicular to P that we got from part B. And then we divided by its magnitude to get a unit vector in that direction. Okay, so just to recap, here we have our two vectors and we used our basic properties. Vectors that are collinear or parallel okay, are scalar multiples of each other. So that's how we solve that one. Vectors that are perpendicular are have a dot product of 0. Okay, and then with any vector, I can always create a unit vector in that same direction by just dividing by its magnitude. Okay, that's it for this one.